Assalamu alaikum, students. My name is Mr. Ahmed Ahmad, and in today's presentation, I'll be going through the Grade 10 Advanced Physics Term 3 2024-2025 Heykel revision. In full disclosure, the file I'll be using today to revise the Heykel with has not been prepared by me, one of the teachers from this school. He or she has shared this file, and it is what I will be using in today's presentation. Also, I'd like to preface the presentation by saying that this will not be an in-depth revision. I will just very briefly go through each of the questions, and if I feel anything is noteworthy in that question, I'll just very briefly discuss it. Okay, let's begin. Here are some equations we may be using today. Of course, the Heykel is divided into two sections, part 1 and part 2. Part 1 consists of multiple choice questions, which you will be doing on your computer, inshallah, in school. And part 2, I think it's 4 or 5 open-ended questions. We also call them free response. Let's begin with question 1 from the multiple choice questions. So part 1, multiple choice. The first question reads, explain how the relative motion between a conductor such as a wire and a magnetic field causes an induced EMF. So if we just take a look at this figure here, in order to induce an EMF, electromotive force, which is not a force, by the way, it's a potential difference, you need a few ingredients. Number 1, of course, you need a conductor for this EMF to act. You need this conductor to be moving relative to a magnetic field. So you need, number 1, a conductor, which in this case is a wire. Number 2, relative motion between the wire and the magnet. And number 3, the magnetic field itself. So if you have these 3 ingredients, you will have an EMF. Another way of thinking of it, you need a wire to cut through magnetic field lines in order to induce an EMF. This EMF, of course, can be found using this formula. EMF equals BLV sine theta, where EMF in volts equals the magnetic field strength, B, in Teslas, the length of the wire inside the magnetic field in meters. V is the speed, the relative speed between the wire and the magnetic field, and theta is the angle between the motion of the wire and the magnetic field. Of course, if we have a potential difference, this potential difference will force, quote-unquote force, the charges to move. Of course, the flow of charge we have seen in the previous trimesters is also known as a current. We can calculate or determine the value of the current using this formula, where I equals EMF divided by the resistance mentioned in the question, of course. Okay, this is since EMF is also or is a potential difference, then in fact this is just Ohm's law rewritten. Let's have a look at one of the questions. Maybe let's go with question number 1. You move a straight wire that is 0.5 meters long at a speed of 20 meters per second vertically through a 0.4 Tesla magnetic field pointed in the horizontal direction. Question A says, what is the EMF induced Question B says, if the wire is part of a circuit with a total resistance of 6 ohms, what is the current? So let's analyze this question. What are my knowns? What are my unknowns? So I know the length of the wire. I know the speed of the wire. I know the magnetic field strength. And if we analyze this very closely, you can also determine the angle between the motion and the magnetic field. The question says that the wire is moving vertically. So we can use, for example, the axis XYZ to help solve this question. So vertically would be the motion is in the Y direction and the magnetic field is in the X direction. So the angle between the X and the Y, excuse me, the angle is 90 degrees. They are perpendicular to each other. We can plug these values into this formula and we can use the formula to determine the value of the EMF. For part A. For part B, the wire is part of a circuit with a total resistance of 6 ohm. What is the current? So in addition to the EMF, now we know the value of the resistance. We can plug it into this formula to find the current in amps. I have a simulation here. We can see this. Here we have a straight wire moving in a vacuum. So there's nothing around it. And here we have a small galvanometer. So this detects the presence of a current currently, meaning at the time being, there is no current detected. However, if this same wire moves through a magnetic field perpendicular to the magnetic field, in this case, the motion is perpendicular to the magnetic field, then there is a current detected. Of course, this current is a result of the EMF induced in the wire. This direction depends, of course, the direction of the current. I'm referring to the direction of the current depends on the direction of the motion and the direction of the magnetic field as per the right-hand rule. So let's switch the direction of the magnetic field and observe what happens to the direction of the current. You can see that it's reversed. Moving on to question number 2. Explain how relative motion between a conductor such as a wire and a magnetic field causes an induced EMF. We've already covered this in the first question, basically. To apply the right-hand rule to determine the direction of the induced EMF and thus the direction of the induced current in a wire moved in a magnetic field. So what's new here is how do I apply the right-hand rule? The right-hand rule is given here. Okay, this is the right-hand rule. You hold your right hand in this configuration, so your thumb is spread away from your fingers, and your fingers, they're touching each other, and the angle between your thumb and your fingers should be 90 degrees roughly. So bend your thumb as much as you can in that direction. Now let's see how to apply the right-hand rule. So line your thumb with the direction of the motion of the wire. Line your fingers with the direction of B magnetic field, and the resulting EMF, here it says F, but they're referring to the electromotive force, so it's actually EMF, corresponds to the direction of your palm. So let's see if we can determine the direction of the current in this simulation here. We'll click pause here. Maybe go back in time just a bit. Okay, so here we have the simulation illustrating a wire moving through a magnetic field. The red pole here, as we can see, the red pole represents a north pole and the blue pole represents a south pole. We know that the magnetic field is from north to south, and we know that the motion of the wire is upwards, So what would the direction of the current be? We can take this from a 2D perspective. Go this direction. So the magnetic field is from right to left. The motion is from down upwards. Let's go back to the right-hand rule. So my thumb should point in the direction of motion, in this case upwards. So my thumb is up. My right fingers, of course, should be pointing to the left with the magnetic field. So thumb up, fingers to the left. If you apply the right-hand rule correctly, your palm should be facing your face, facing towards you, pointing towards you. So the current would be moving out of the page. The current would be moving out of the page. So the current would be moving in this direction. It will enter to the red segment of the wire. It will enter into this terminal of the galvanometer. And in theory, it should push the little arrow here, this detector, to the left, which is negative. Okay, let's move on. Question number 3, relate effective current and effective potential. I think here they mean potential difference to the maximum values of current and potential or voltage, yes, in an AC circuit, and calculate the maximum and effective values of current and potential and power for an AC generator. So just bear with me. So let's go to an AC circuit. So in AC, the current alternates between positive and negative. We can see this in this simulation over here. I can go to AC generator, click play, and we can see that the current, it's alternating between positive and negative. I can also display this on an oscilloscope. Okay, so this traces what happens to the current as a function of time. So we see where the horizontal line I'm pointing at exactly, this represents the 0 line. So the current is alternating about this line. So it's going between positive and negative. Now there are a few values you need to be able to determine from this plot here. So this plot is represented here in this graph. So the maximum current achieved is called Imax, and the effective current, I effective, I'll not get into the significance of I effective. We will just, in this presentation, see how we can determine its value. So Imax, it's easy to identify. Just look for the maximum value, not on the scale, not on the grid, the maximum value of the curve itself. This is Imax. Now, how do I find I effective? I effective or IAC is found, or IRMS, these are all synonyms for the same thing, meaning the same thing, equals 0.707 times the value of Imax. You might have seen a different formula. Instead of 0.707, you might have seen this value, square root of 2 over 2. If you plug this into your calculator, square root of 2 over 2, it will give you 0.707. So it's the same. It's the same. So that's how you find effective current. And the same is true for effective voltage or effective potential difference. The VRMS, you find it the same way. You take the peak voltage, which is the maximum voltage, and you multiply it by 0.707 and calculate maximum effective values, current, potential difference, and power for an AC generator. Now, the only one which stands out between these quantities, namely voltage, current, and power, is power. Because power is unique in that even in an AC with an AC current, power is always positive. I'll not get into why it's always positive, but it's always positive. And the maximum power, again, we read it in the same way we would read maximum voltage and current. I look for the highest value in the curve. However, the average or the AC power is a little bit different in calculation than finding voltage and current. You don't multiply by 0.707, you just multiply by half. So for instance, if the maximum power here was 20, the average power would be 10. Question number 4. Explain how transformers are used in the national grid system to transmit power through long distances with minimal power loss. Let me just look for the slide. Okay, so when we want to generate power, of course, the objective is to supply to an end user. This could be a home, it could be a factory, it could be anything, a residence, building, anything. So this is my generator. This is where we are generating electricity. And this is a home. This is the end user. This is who wants this electricity, wants to receive this electricity. Now, when we send this electricity through wires, there will be a power loss. And the power loss can be determined using this formula. Power loss equals the current running through the wire squared times resistance. Of course, the higher the power loss in the form of heat, of course, the less power ends up being used by the user. So I'm generating power which is being wasted as heat. This is undesirable, of course, because effectively we're losing money. Now, how can I reduce this power loss as much as possible? To reduce the power loss, you can either, your options are to minimize the resistance and or to minimize the current going through the wire. Without going too in depth as to how or why, but one of the ways to reduce the current is by increasing the voltage. So by increasing the voltage, we decrease the current. And if we decrease the current, we decrease the power loss, which is desirable. This is a good thing. So again, how can I reduce the power loss? Is by one of the methods or one of the techniques we use is decreasing the current. How can I decrease the current? By increasing the voltage. Now, what machine is used to increase the voltage? And the machine is called, or the machine we've studied, which increases the voltage and at the same time decreases the current, is a transformer. There are two types of transformers. We have step up and step down transformers. So let's take this example. These are arbitrary numbers. You don't need to remember them. They may or may not be correct. So for example, we have a generator. Of course, it needs to be AC because transformers, they'll only work with AC. At least, yeah, let's say for our purposes, we will assume that only AC is running through the transformer. So it's only running in AC. Let's say power is being generated or electricity is being generated at 10,000 volts. This would correspond with a relatively high current, which is undesirable, as we said, because as this current is moving large distances, to result in a lot of wasted energy in the form of heat. So how can I minimize this power loss? It is by reducing the current. In order to reduce the current, we need to step up, meaning increase the voltage using a transformer. So you'll see many different values. As I said, these are arbitrary values. Here we stepped up the voltage from 10,000 to 220,000. This could be more or less depending on many factors. And by increasing the voltage, I did not write it here, but what has happened is we substantially decreased the current, reducing the power loss. To long distance, yeah. Of course, you can read through all this. Feel free to read all this. Question number 5. Relate the turns ratio of transformer to its corresponding voltage ratio and apply the ideal transformer equation to solve numerical problems. So the transformer equations, they're quite straightforward. Let's just quickly have a look. Again, we have two types of transformers, step up and step down. Step up transformers, actually, before I get to the distinction between the two, let's just discuss what they have in common. They have a core. A core in our curriculum. Typically, this core is a conductor. Typically, in our curriculum, does it have to be the case? Not necessarily. It's just our curriculum. We have a core, shared core, and we have two ends of the transformer: a coil, or a coil here known as a primary side, and a coil here known as a secondary side. This is shared between the two. Now, how do we assign these names, primary and secondary? It depends on the direction of flow of electricity. So if electricity is being generated here, and it's being sent to the right, or it's being the current is flowing to the right, from left, I mean, being generated here, and the end user is somewhere over here, then the primary side will be closer to the generator, and the secondary side will be closer to the recipient of the power. If we look very carefully and analyze this figure, you see that on a step-up transformer, the number of coils, or the number of turns in the secondary coil, is greater than the number of turns in the primary, 20 versus 5. This is the opposite, or the opposite is true with a step-down transformer. Now let's look closely at what happens to the voltage, current, and the power. If it is an ideal transformer, meaning there are no losses happening in the transformer itself, then the power entering equals the power exiting the transformer. However, if it is a real transformer, unfortunately, there will be some losses. We'll go through the Heykel, see if a real transformer is mentioned. طيب, where do these values come from? You'll notice that the product of the current and the voltage, so current times voltage equals power. And this formula you should know, P equals IV. This is true for both the primary side and the secondary side. So 10 times 100 is 1,000, 2.5 times 400 is 1,000. Again, this is true for ideal transformers, where there are no losses happening in the transformer. I'm not discussing, or I'm not referring to what's happening in the wires. Now let's see the distinction between them. Like we said, the number of the turns and their goal. The step-up transformer, if you look carefully, increases the voltage while decreasing the current. This is the main goal behind the transformer. In a step-down transformer, the opposite is true. We step down the voltage while increasing the current, and the power is maintained. The power is maintained on both ends. Let's have a look at the transformer equations. These are the transformer equations. VP, which is the primary side voltage over the secondary side voltage, equals NP over NS, which is the number of turns at the primary side over the number of turns in the secondary side. This is known as the turn ratio. We see that the turn ratio is equal to the voltage ratio. The only quantity which differs is the current. So here we have PPS. So current is the opposite. Moving on. Sorry. Moving on. Define electromotive force and specify its units. We already discussed what's EMF, but let's just quickly read through. Induced EMF is a potential difference. Again, it's not a force. It is a potential difference across a wire that results from the production of an electric field. And this is his formula to find the value of the EMF. Moving on. Explain how the speed of propagation of electromagnetic waves vary through different materials. So a wave, specifically an electromagnetic wave, its speed depends on the medium it's moving through. How do I calculate the speed of a wave depending on the medium? We apply this formula, where V equals c divided by the square root of k. V is the speed of the wave. V is the speed of the wave in the medium. C is the speed of light in a vacuum, which is this value. Typically, we round this up to 300 million meters per second, typically. So 3 times 10 to the power of 8 meters per second. But if you want to be totally precise, that's the value. But what is k, square root of k? Let's have a look at what the square root of k is. So square root of k is the relative dielectric constant. That's k. Again, it depends on the material. This may be given directly, or you'll need to work it out from the index of refraction n. So if you were given the index of refraction n, then you can find k, and then you can plug k back into this formula to find the speed of light in that particular medium. Of course, k in a vacuum is 1. So if you were trying to determine the speed of light through a vacuum, you would plug in v equals c over the square root of 1, which equals c, which makes sense. The speed of light through a vacuum equals the speed of light through a vacuum. Makes sense. In air, the value is a little bit, of course, I'm referring to the dielectric constant. The value is a little bit greater. If you plug that in into this formula, then you will get a slightly smaller speed than you would see for a vacuum. Moving on to question number 8. Apply the wave equation to calculate the wavelength, frequency, or speed of electromagnetic waves. The wave equation in our level, written advanced, is, let me see if it's in this formula sheet here. Yeah, it's this formula here. Lambda equals c divided by f. It can also be written as, here this, it also can be written as v equals f lambda. V equals f lambda. V equals f lambda. Again, here it's written as lambda equals c over f. So what do these terms refer to? Lambda is the wavelength. F is the frequency. And c in this case refers to the speed, but this term c is generally reserved for speed of light in a vacuum. However, we're not sure if the electromagnetic wave is traveling through a vacuum. That's why I prefer the term v instead of using the term c. Okay, it's more general. It's not just specific to motion of a wave in a vacuum, or propagation of wave in a vacuum, rather. And the only thing I think is notable here would be the relationship between f and the period. So if the frequency isn't given directly, you can find the frequency from the period by using the formula f equals 1 over t, t being the period. Moving on, question number 9. Determine the optimal length or orientation of an antenna for the best reception of a given wave. Okay, so here we have an antenna. No, we don't. Here we have an antenna. This is an antenna used to transmit a radio wave, and on the far side we have an antenna used to pick up these radio waves. So let's click on electric full field, and let's change this to oscillating. So this is the electric field as it's being generated. Of course, how do we generate this electric field? By accelerating an electron. In this case, there's an AC supply hooked or connected to the antenna, which will cause the electron to oscillate up and down, up and down. This will result in a electric field. Just a second, boys and girls. Yeah. So the acceleration of the electrons, no, not here. My apologies. Yeah, over here. So when we hook up an AC supply to an antenna, this causes oscillating potential difference, which accelerates the electrons up and down, as we saw in the simulation. This generates an oscillating electric field. This field, electric field, will cause or result in a magnetic field, which is not shown here because it's perpendicular to the electric field. This is the electric field that's being generated as the electrons oscillate in the antenna, and the resulting magnetic field, I'm trying to find it. Yes, here it is. So here's an electric field oscillating up and down, up and down. Perpendicular to it, we will have an induced magnetic field. Electric field, perpendicular to it, we will have an induced magnetic field. So again, what direction does the electric field oscillate? In the same direction of oscillation of the electron. So let's go back to our simulation here. Our electron is oscillating up and down, so the electric field will be oscillating. The electric field will be oscillating up and down. Perpendicular to it, which will be invisible because this is a 2D perspective, will be a oscillating magnetic field. The magnetic field will be oscillating in this case in and out of the page. In and out of the page. So that's when it comes to orientation. Now, your receiver, this antenna, ideally it should be lined up such that if the electric field is oscillating, let's say in this case in the y direction, your receiving antenna should be aligned in the same direction. So it should also be pointing in the y direction. So let's read this question just for a little bit clarification. Radio antennas normally have metal rod elements that are oriented horizontally. So here they're saying that the antenna is aligned horizontally. From this information, can you deduce the direction of the electric field in radio signals? Yes, the electric field will be aligned with the antenna, horizontal. Conversely, the magnetic field will be aligned vertically because it's perpendicular to it. And as for the optimal length, the length, I have it somewhere here. Optimal length, just bear with me. No. Yeah, it's here. So there are types of antenna as per your book. Either the receiver is attached to the middle of the antenna. So if we read this, let's read this point here. When the receiver is connected to the, when the receiver is connected to the end of the antenna length is 1/4 of the wavelength. So let's look here. Here in this little sketch I drew, we have an antenna and the receiver is connected to the very end. In this case, the length of the antenna, which will give me the maximum efficiency, equals the 1/4 of the wavelength of the wave we are of the radio wave we want to pick up. And as for the second case, yeah, here it is. If the receiver is in the middle of the antenna, like in this sketch, then the best best length when its length is half of the wavelength. So L equals half of the wavelength. Maybe you could pause the video, read this in more in depth. So let's maybe go through this question. I found this question interesting. Would an FM antenna designed to be most sensitive to stations near 88 megahertz be shorter or longer than one designed to receive stations near 108 megahertz? Of course, here the value given is, this is frequency, and wavelength is inversely proportional to frequency. So this has a longer wavelength than this. This value has a longer wavelength than this. Since it has a longer wavelength, or longer than, yeah, this will have a longer wavelength than this. So which one would have a longer antenna? The one with the longer wavelength. So this would have a longer wavelength, meaning it would need a longer antenna. Again, where is this? This is right here. L is a function of wavelength. The longer the wavelength, the longer L, regardless where the receiver is placed. This is true for both designs. So moving on, question number 10. Recall the concepts of constructive and destructive interference and define interference fringes of light. Okay, so we have coherent light passing through two slits. And as the light, actually I have a simulation here somewhere I could show you. Okay. So let's pause that. So coherent light passing through two slits. Let's assume these are two slits, and the waves will begin to propagate through and move through these two slits. Now, what do these lines represent? So let's just focus on one slit here. We have one slit. This line, this black line, what does it represent? Without going in depth, this represents the crest of the wave, while the white part represents the trough of the wave. So the same is true with the other slit. The black line represents the crest and the white line represents the trough. So if we look at the points of intersection here, this point of intersection, this point of intersection, this. These points represents points where the crest of the wave produced from slit 1 lines up with the crest of the wave produced at slit 2. Since the crests are aligned, then we have waves which are in phase, meaning we'll have constructive interference. Light interfering constructively will result in a bright band. While if we look very carefully, here we have a red line aligned or corresponding in position or existing in the same place as, so the crest from S1 is aligned with the trough from S2, so you'll have destructive interference. So if we trace all these points, then we'll have a dark band because this is the result of destructive interference. So look very carefully at this figure here. Question 11. Explain how bright and dark fringe are creating double slit interference investigation with monochromatic light. Same. Moving on. Discuss the phenomenon of thin film interference as one example of light interference in nature and explain how the refractive indexes of the mediums that make the thin film control wave inversion. Okay. So in thin film interference, this is thin film interference. You might have observed this sort of pattern if you looked at some petrol or some oil spilled on the floor, or if you have seen soap bubbles under correct lighting, you might have seen a similar pattern. we have this interesting pattern of bright and dark colors. Now, where do these come from? Where do these come from? Okay, so we need to break down what's going on into a 2D view. So here I'm looking from the side. Now we have typically three mediums: medium 1, medium 2, medium, or in this case, a middle medium, and then medium 2. The middle medium, we always refer to it as the film. Light is incident. This light is partially reflected when it meets the boundary between medium 1 and the film. This is known as ray 1. And partially transmitted and then reflected again as it meets the boundary or reaches the boundary between the film and medium 2. This is known as ray 2. And you the observer here, you will observe a bright or dark color depending on whether or not ray 1 and ray 2 were in phase or out of phase. If they were in phase, then we get constructive interference. You will see a bright color. If they were out of phase, then they were then destructive interference will take place. You'll see a darker color. Now, what does this depend on? It depends on several factors. One is the thickness of the film, and two, whether or not ray 1 and ray 2 were inverted or not inverted. Now, what does inversion mean? Let's take a look at this figure here. This is one of my freehand sketches. Now, we have an incident ray. It's moving downwards, and it meets a boundary between two mediums, and it will be reflected. It will be reflected. In both the cases I drew, right and left, they are both reflected. Now, if you look very carefully at where the wave is in contact with the surface or with the boundary, then the crest, if you look very carefully, the crest is pointing to the right. Okay, the reflected ray or wave, the crest is pointing in the same direction, to the right, same orientation, so to the right. In this case, we say that this ray is reflected but not inverted. Compare this to the second case, this case over here. We have an incident ray. Again, the crest is to the right of the axis. It's to the right. However, in this case, the reflected ray, the crest is on the left side. So they're both reflected, but one is this is inverted, and the one on the left is not inverted. Now, how can we determine or ascertain whether or not the wave will be inverted or not inverted? It depends on the refractive index of the two mediums, in this case, medium 1 and medium 2. If the refractive index decreases, so N2 is smaller than N1, then the reflected wave is not inverted. However, if it increases, then the reflected wave is inverted. Let's move on. Explain formation of color spectra when white light is used in double slit. Explain how coherent light is generated. Okay. What is coherent light? Coherent light is light where all the waves are in phase and all the individual waves have the same frequency. Now, if you can have monochromatic light which has only one frequency, but it could be out of phase. How can I cause all the waves? How can I have them all line up, meaning be in phase? We pass them through a single slit. I won't go in depth into this. Explain the formation of color spectra when white light is used in a double slit investigation. Let's go to a double slit investigation. Compare. So you can read through this, see monochromatic light. If we pass it through a narrow slit, it becomes coherent. Have a look here. let's see, compare between different colored lights going through a double slit. So here is green, red versus white. White, you observe that you observe many different colors. Why is this happening? This is because white light is a combination of light waves with different wavelengths. And these different wavelengths waves overlap on the screen. They interact and interfere, creating this effect. Where were we? We were here. Question 14. Explain diffraction of light according to Higgins' principle. All the points of a wave front of light can be thought of as new sources of smaller waves. Yeah. So diffraction. So diffraction is the spreading of light or a wave. So here we have a wave passing through a narrow opening. It starts to spread. Of course, this effect depends on many factors. One of them being how wide the opening is and the geometry involved, etc. Now, one of the ways to explain diffraction is by referring to Higgins wavelets. What are Higgins wavelets? So a single wave front. So let's consider this crest, the frontmost one being the wave front. This is actually, it's not just one continuous wave. It's actually made up of tiny, what we call wavelets, Higgins wavelets. To be fair, I don't know the correct pronunciation. I pronounce it as Higgins. Is it Huygens? Is it Higgins? I'm not sure. Anyways, let's stick to what's important here. So these wavelets, each of them will behave as a new source of light. So if we go back to this simulation here, so instead of having two slits, you can just understand this as two separate wavelets. They're both creating their own waves, and you'll see a similar pattern to what we saw with the double slit experiment. There are some differences, but the fact that we have bright and dark colors is similar. Define diffraction as the bending of wave as it passes through the edge of a barrier, and how the diffraction pattern is created passed through a single slit with illustration of Higgins wavelets. I believe we did this. Now for the free response, EMF equal BLV sine theta, I equals EMF over R. We already discussed this. Define electromagnetic induction. Identify its type. Self-induction, mutual induction, or relate them to Faraday's law of electromagnetic induction. Let's work backward here. So Faraday's law is when you basically in essence, when you have a wire and this wire cuts magnetic field lines, as we saw. So the wire is moving relative to the magnetic field. You will have an EMF induced. We know how to determine that value. Now, mutual induction and self-induction. Let's talk about mutual induction. Mutual induction. Actually, let's go to what's more difficult, self-induction. I have it here somewhere. Yeah, so self-induction. So let's consider this circuit here. We have a battery, we have a resistor, and we have a coil. Absent is a switch. However, I did get into a switch over here. So what happens when you open and close a switch in this circuit? Before we actually discuss what happens when a switch is connected, let's just quickly discuss what happens when a current runs through a coil. When a current runs through a coil, actually, let's see what happens when a current goes through a coil. So here we have a coil connected to a battery. Now, when I connect this battery to the coil and the potential difference begins to increase, then a magnetic field will be generated around this coil. Of course, the size or the strength of the field depends on the current flowing through. So the greater the current flowing, the greater the strength of the magnetic field. This is an important factor here. So let's go through this in detail. So when you close the switch, meaning the current begins to flow through the coil, flow through the coil, the current will begin to flow through, the magnetic field will begin to increase in size, grow in size. As the magnetic field grows in size, the magnetic field lines will begin to be cut as it's growing. Think about it. There's relative motion between the magnetic field and the coil. This relative motion will result, again, relative motion of wire and magnetic field will cause a EMF to be induced. Now, this EMF, according to Lenz's law, will always be in a way that it opposes the process which created the magnetic field. So let's say that again. Let's go back to the simulation. Okay, now this side is positive of the battery and this side is negative. So the current is flowing from this terminal through the coil and back to the negative terminal. So when I close the switch, meaning I activate the circuit, a current will begin to flow from the positive side through the coil to the negative side. A magnetic field will begin to grow. Now, Lenz's law says that we want to oppose the change that's taking place. The change taking place is a growing magnetic field. So how can I oppose this change? Is I have to work against whatever created the field. What created the field in this case is the battery. So an EMF will be induced opposing the battery. So the EMF will work against the battery. So the induced EMF will be such that it is in the opposite direction of the potential difference of the battery. So let's see if this is the case. So when we close the switch, the induced EMF is in the opposite direction. Now let's go back to the simulation and see what happens when we open the switch. So now we have an operating circuit with a already existing large magnetic field. Now when we open the switch, now we're opening the switch, the magnetic field begins to shrink. Now, Lenz's law tells us that there will be opposition to any change. The key word here is change. So we already had a pre-existing magnetic field, which is currently, or at the time being, shrinking. Now, Lenz's law says that something will take place which will combat this or oppose this change. So it will try to reinforce whatever was creating the magnetic field in the first case, which was the battery. Therefore, the induced or the self-induced EMF will be in the same direction as the battery. Complicated? Yes, it is. Differentiate between step-up and step-down transformers. We discussed. Explain how the relative motion between a conductor such as wire magnetic field causes induced EMF. We already discussed. Question number 3, part A. Define electromagnetic induction. We've seen it. Mutual induction, like in transformer. Relate them to Faraday's law. B. Lenz's law. Affect the operation of electric motors and generators. This is new. Magnetic levitation, breaking effect through eddy currents. Applications on Lenz's law. Differentiate between AC and DC. Point 3 we already discussed. DC is direct current, where the current is flowing in one direction. AC, the current is alternating between positive and negative. And these are the two generators we saw in the curriculum. No, this is a motor. This is a generator. This is a DC generator because the current only has one polarity, in this case, negative. And I will not go into the breakdown of what this generator, the component names are. And this is an AC generator. So AC and DC we've already covered. Let's go back. Let's look at Lenz's law, how it affects motors and generators. I have this summarized, I think, somewhere. Maybe here. Yeah, so Lenz's law, we have Lenz's law in motors and generators. So let's just quickly read through this. Lenz's law, of course, is always opposing motion. Lenz's law, let's have a look at what Lenz's law is. Lenz's law says that the magnetic field produced is in the direction such that it resists the change that causes. So it's always trying to oppose whatever caused the magnetic field to exist. Okay. Like, let's see what happens Lenz's law in a motor. So suppose we have a current of I1 flowing through a motor's armature. You can do this. Let's click motor. Don't know what this is. Okay, so here we have a motor. Or do we? How do I stop this? Okay. So here we have a motor. Here we have a motor. And at the time being, there's one current flowing through, which is I1. Now, as this motor begins to move, it's moving. So we have motion of a wire through a magnetic field. We will have a new induced EMF, which will oppose the motion which created it. So they'll be in the opposite direction. So I1 and I2 will be in the opposite direction. So the total current flowing through the wire will be less as the motor is moving. So this is how Lenz's law affects a motor. You can pause and read through this. Of course, I wrote current, but in reality, it should be EMF. But let's see how it affects a generator. But let's go to a generator. So this is a generator. So spinning a generator causes a current to be induced in the circuit's wire. So as we're moving this generator, as we're moving it, we have relative motion between a wire and a magnetic field, which will result in or induce an EMF. A magnetic field will be generated in the armature's wire. So let's pause just for a second, see what's going on. So if we go in 2D perspective, it doesn't show, unfortunately. So now we have a current flowing through the wire. This current, if we click here, I could show you. Yeah, pause. So this current flowing through the wires will induce a new magnetic field. So now we have two magnetic fields. The one from the permanent magnets and the one as a result of the current flowing through the wire. The resulting magnetic field will exert a force resisting motion of the generator. So the two magnetic fields will now interact in a way which they will, cause or result in a resistive force on the generator. What is the net result? The net result is the Lenz's law in a generator has the effect of making the generator more difficult the faster you move it. So what happens is, again, just quickly recap, Lenz's law in a motor, the total current decreases. Lenz's law in a generator, the faster you spin it, the more difficult it is to spin. Where is the Heykel? Okay. Motors and generators. Braking effect and Lenz's law. This is quite straightforward. I'll not get into Lenz's law in a coil. That is just way too complicated for the time being. Let's just take this picture very briefly. Just a second here. Okay, so here we have a wire being pulled through a magnetic field in green. So this is a pre-existing magnetic field in green. It's being pulled to the right. So there's motion of the wire to the right. So we have motion in the presence of a magnetic field. This will induce an EMF. The EMF in this case will result in a current flowing downwards. Now the current flowing through a wire will result in a magnetic field. We can see the magnetic field in blue. Okay, the dots, of course, represent the magnetic field in this area here, flowing out of the page, and then it goes around and into the page. So if you look at a 2D perspective from the top, so 2D perspective from the top, what you would see is circles representing the magnetic field. So now we have two magnetic fields. According to Lenz's law, these two magnetic fields will interact in a way which will oppose motion. So in essence, you're pulling to the right, you will experience a resistive force to the left. Okay, braking effect. Yeah, now this can be translated or applied to even an object moving circularly. It doesn't have to strictly be an object moving in a straight line. So so what if we don't have a wire? What if we have some sort of plate or a disc moving? So here we have a disc moving. Here we have, here we have a plate moving. Here we have a disc rotating. Now, so far we only looked at the conductor being a wire. What if it was this configuration? It doesn't matter. The same physics applies. Motion inside a magnetic field will induce a current. But since this current isn't flowing through a wire, it will move in this uncanny way, this strange pattern. And these are known as eddies or eddy currents. Eddies or eddy currents. Okay. Now, how do these eddy currents affect the motion of this disk? For instance, we have eddy currents flowing through the disk or in the disk. Current flowing through a conductor will result in a new magnetic field. These two magnetic fields, the pre-existing magnetic field and the newly induced magnetic field, will interact in a way which will resist or oppose the motion which created it. This will cause a braking effect, or the disk will begin to slow down, or at the very least experience a resistive force. Moving on, question number 4, which is, I believe, the second to last question. طيب. Apply lambda equals xd over L to calculate the wavelength or to find an unknown distance. So in the double slit experiment, lambda is the wavelength, x is the distance between the middle band and the band you're investigating. If m equals 1, which is the case in this in the way this formula is written, m is 1. So we're going to the first band, and L is the distance between the slits and the screen. L is the distance between the slits and the screen, and D is the slit separation. Show that the intensity of the bright band decreases as you go further from the central band. So this is the central band. This will be the brightest. The further up you go or the further down you go, the less intense, the less bright the bands will be. Explain the formation of a colored spectra when white light. We discussed this. Explain how optical discs act as a diffraction grating and using the constructive interference equation m lambda equals to calculate the wavelength of light. So this is covered in an example in your book. So there are two types of diffraction gratings. There's the reflection type and there's the transmission type. In the reflection type, the incident light strikes or meets the diffraction grating, and upon reflection is diffracted, so spread into different distinct rays. Now, if you look very carefully at the CD or DVD surface, there are these tiny ridges which resemble the ridges you see in a diffraction grating. So that's why they behave the same. Now, I would suggest you go through this example. It's somewhere in your book, example number 3, I believe, and go through the solution. Go through the solution. It should cover all of this. And for the last question, explain how bright and dark interference fringes are created in double slit experiment. Discussed. Constructive, part 2 is discussed. Part B, define coherent and incoherent light. So coherent light is light in which all waves have the same frequency and they're in phase. For example, this would be a laser. Incoherent light, they may or may not have the same frequency, but they also are out of phase. So for example, sunlight. So look here, we have non-coherent lights, in this case monochromatic. So all the lights have the same frequency since they're monochromatic. However, they are out of phase. In this case, it's non-coherent. And on the very right, we have a big variation. They have different frequencies, and they are naturally would be out of phase. Any more questions in the Heykel? No? Okay, we'll wrap up. This has already been long enough in terms of a revision session. I would like to just make just one note, just say one more thing. I know, boys and girls, this may not have been as in-depth as you would have liked. Reason being, we have a limitation, which is time. This has already been an hour and 10 minutes, and we barely scratched the surface. I hope you appreciate that going through an entire Heykel in 30 to 40 minutes is very difficult. I did the best I can. I hope you benefited. I hope, I wish success upon all of you, and please go through the Heykel in more detail. This file, however, unfortunately, I cannot share because I don't have you as contacts. Ask your teacher, he may or may not have it. She or he may or may not have it. And yeah, this was Mr. Ahmed. All the best to you. أدعو الله لكم بالتوفيق والسلام عليكم ورحمة الله وبركاته.